Hello everyone, welcome to AI Plus Club Unilive Virtual Bootcamp. Get started with machine learning. I'm Okoyemi Bamibade, a data scientist and a machine learning engineer at Data Science Nigeria. My work revolves around researching and AI product delivery. I'm also the AI Plus Club Unilag lead, and I'm a final year student of systems engineering in University of Lagos. So you can follow me at Opeyemi Bami on Twitter. You can look at some of my posts on Medium and also check some of my work on GitHub. So today we'll be looking at feature engineering. On our content, we have what is feature engineering. We look at the meaning of feature engineering. We look at feature understanding. Under that, we look at categorical and numerical. Look at the 4 levels of data. Feature importance, exploratory data analysis, how to remove or if at all to remove harmful rows. We look at PPScore and correlation. Also, we have how to encode categorical feature. By 5, we'll be looking at feature transformation. We have feature generation and construction. We have feature scaling and also dimension reduction. Are you excited? So let's get started. Okay, so the question here is, what is feature engineering in machine learning? Feature engineering is just the transformation of data into features. You have your what? You have your data. So you're trying to transform each of these features into what? A better representative that represent the underlying problem you're trying to solve. Look at this picture for instance. I have my raw data. With my feature engineering, I can have my features prepared for what? For modeling, isn't it? So why are we doing this? To improve machine learning performance, isn't it? Okay. Now, if you look at feature understanding, we have to look at it from a broad view, which can be categorical data or numerical data. We can also refer to this as qualitative or quantitative, isn't it? So the 4 levels of data here is what? The categorical and numerical. So under the categorical, we can have data to be nominal or ordinal, and the numerical can be what? Interval or ratio. So we'll soon get to know the meaning of this soon. For the categorical, let's start with the categorical. We have the nominal and the what? The ordinal. What's the nominal? The nominal is the least structured data you can have, the least structured features you can have. For instance, look at this. I have pen, pencil, and eraser, isn't it? I have categories of what? Cat, dog, and cow, isn't it? So these are categories of animals. Am I right? Now, what can I do with this in my model? Sometimes nominal features are you can neglect nominal features when you're trying to build a machine learning model at first. And sometimes if your feature engineering skills is solid, you can bring out the best out of what? Nominal features. Now for the ordinal features, they are more structured than the what? The nominal, just that in the sense that they are ordered, isn't it? There is some kind of ordered in what? In this. For instance, we all know that excellent is better than good results and good is better than bad. Also, fantastic is a better what? Comment for what? Than okay and what? Don't like, isn't it? So there's some kind of order here. Example I can look out for here is the linked scale. This is like a linked scale, isn't it? They are both categorical data, but this is having order, why this does not have what? Order, isn't it? Okay. Now, if you look at it from this table, we can look at level of measurement, properties, examples, some descriptive statistics we can perform on this, and the kind of visualization we can perform. If I have the nominal data, Remember, nominal is what? Less structured. Property in the sense that it is discrete and orderless. If you go back to that, you'll see that pencil, pen, eraser, they are all discrete and orderless. There's no difference between me putting eraser first and pencil last, isn't it? That is the meaning of this. An example here is what? Binary response, true or false. There's no difference between me saying true or false or true, isn't it? I can have names of people. There's no difference in calling John before brain. There's no difference between calling girl before boy, isn't it? Right. So some descriptive statistics we can also do on nominal data is what? We can have the percentage mode, that is which category occurs the most. And when we have data set, features like this, the kind of visualization we can do on them are very, very what? Minimal. So example is what? Bar chart. We can have bar chart to represent them. So if you look at the ordinal, we have ordered category. We can have them in order, isn't it? We can also have the, for example, the linked scale. I've mentioned this before on grades. Excellent, good, or excellent, very good, good, bad. So what are the descriptive statistics we can perform on this? We can have the mode, median, percentiles, and the likes of it. And you can see that there are what? More visualization, meaningful visualization on the what? On the ordinal category. So if you look at the interval, for instance, differences between ordered value and what? The difference between ordered value have meaning. What do we mean by that? If I have an ordered value, for instance, if I find the difference between them, it will result in a meaningful interpretation. Does that make sense? So the statistical visualization we can do here are what? Bar chart, pie chart. You will see that as we are moving from categorical data to numerical data, our choices are increasing, isn't it? Okay, for the ratio, we can have the mean and standard deviation. Perform mean and standard deviation. We can have histogram, box plot on that. So let's actually see how this are put together by importing some libraries we'll be making use of. We will use the NumPy, the Pandas, the Seaborn, Matplotlib, PPScore to do some analysis. So the training set and the test set has been imported with what? With pandas.read CSV. I have two set of data sets here. One from Titanic dataset and one from what? Sunday Logistic. The Titanic dataset was taken from Cargo, while the Sunday Logistic was taken from Zinde. If I look at the Titanic dataset, the first 5 rows there, I have some features here. Each of these columns are called features in machine learning. So I have passenger ID as a feature, P class as a feature, name as a feature, sex as a feature, age as a feature, and the likes of them. Each of them are features. If I look at the Sunday train dataset, I have order number as a feature, user ID as a feature, vehicle type as a feature, platform type as a feature. Now, we need to identify each of these features, whether they are what? Categorical feature or what? Numerical features. For instance, you will see that vehicle type is what? Is a categorical feature. Personal or business here is also a what? Categorical feature. If you look at placement day of the month, for some, you can say that it's a what? Categorical feature or numerical feature, in the sense that days of the month can range between 1 and what? And 31 or 30 or even 29, isn't it? So in that sense, we can call this a categorical feature or what? A numerical feature. But the days of the week are strictly what? Numerical, they are strictly categorical features. We also have another feature here, placement time, and the likes of them. So how can we improve this feature? All these features here cannot be used for machine learning directly like this. Some of them, there's no way we can pass this feature directly into machine learning and it will work. What we can do is to what? Do some feature engineering on them. That is, make them better representation of the problem we are trying to solve. So in this case, we'll look at EDA and data cleaning. We'll look at how to identify what if there are missing value in your data. How do we remove these missing values? Inputting for the missing values and using PPS and correlation to look at some what underlying relationship between what features. Now, if you look at the this chart, we have a better way of what of looking at if there will be what missing features in our data. We are just using an heat map to plot the missing parts in what in our data. The trend dot is null will return boolean. This train dot is null here will return boolean, and we are passing it in what the seaborn heat map. So we are doing an heat map, and at a glance I can see all this stripe we are seeing here, they are the missing entry spot. The missing entry, it means that we have missing values in age, we also have missing value in cabin. We have missing value in age and missing value in cabin. This is the Titanic data set. So with this arc here, I can quickly see where I'm having missing values in my what in my data. Now, if you want to look at the percentage of the missing value, you will see that we have for the age, we have 20% missing, and for the cabin, we have about 78% missing. Wow. So it means that majority of the entries in the cabin feature are empty. How can we undo that? With visualization, you can see also at a glance that for the age we have what 20%, and for the cabin we have 78%, about 78%. So it is better to always use visualization so that at a glance you can see where the data are missing or so. If you do investigation on if you do some experimental data analysis on the Sunday data set as well, you see that we have missing value on the temperature. We also have missing value on the perception in what precipitation in millimeter. So you can see also that several, in fact almost 90%, if not 100, of the precipitation in millimeter is missing. How do we undo this? Should we drop this feature entirely or try to put some value for the missing value? How do we do this? There are several techniques you can use to undo missing value. Different ways of handling missing values depending on which work best for you. We can decide to remove the observations that are having missing value. In this case, it means that we will be losing about 90% of our entries. By the time I remove all these ones that are missing here, it means that my data set will be very, very small at the end of the day. Now, another way is to perform mean or median imputation or implementation of mode or frequency category. There are many ways you can use to handle the missing value. You can capture the missing value in a bespoke category. You can replace missing value with a value at the end of the distribution as well. So again, if I look at the percentage of the missing value in Titanic dataset, for the cabin 77 and for the age 20%. How can we handle this? Let's look at it from the statistic perspective. We can do some statistical imputation based on distribution. We can also do some comparison, which we're going to do later in the day with PPScore and correlation. Now, if I look at the distribution, if I pick a feature out of the data set, for instance, the age feature, and I look at the distribution, this is almost a Gaussian distribution. I believe we are familiar with Gaussian distribution, and the majority of the machine learning algorithm assume that your data is Gaussian-like. Okay, so if this is more like a Gaussian distribution, it means that the missing value in age, I can try to impute them with the mean of the age, with the age column, or the median of the age column. So with this code here, I'm trying to create a dataset list having the train and the test, because I have two datasets, the train and the test. The train is what I'm using to train, and the test is what I'm trying to get prediction on, isn't it? So from scaling, we import the simple scalar. The simple scalar can be used to do some statistical input. For instance, we are using the strategy here, and the strategy here is what? Is the median. We are using the median. It means that for the age what? For the age feature, any missing value any missing spot that we have there, use the median of the age feature to represent those what? Those missing value. And if we do that, sorry about that, if we do that, it means that at a glance here, I don't have any missing value again on the age column. I can do the same thing for the cabin, but there are some things we need to consider here. The cabin feature, almost everything is gone. How do we do that? It will be better if we entirely drop this what? This feature. That is, we don't want to even use this feature at all in our modeling, because if we try to do some individual missing value imputation on this, it will end up introducing another distribution entirely in what? In the data set. So it will be better to drop the what? The cabin feature. Now, we said we can do some comparison. We don't know whether we can use the mean, median, standard, mean, median, mode. Which one works best for our features? So with this code here, this code is actually gotten from Machine Learning Mastery. So I'm importing NumPy, from NumPy, I'm importing mean, standard deviation, and risk CSV. I have this simple model. I have the random forest classifier to quickly check which imputation is better. I'm doing cross validation, and my data set is from where? I'm downloading my data set from net for this particular feature for this particular example. Now I create a what? A data frame by reading read CSV, pandas read CSV from this, and we now have our feature as X, and we have what? Y as our target. Don't worry if you don't understand this. By the time we are doing our regression analysis or classification analysis, you will understand better. Now, if I run a simple model on that data set, I'm trying now to check whether the main strategy is better for my data set, or the median, the most frequent, or constant. The result is here. For the mean, I have 84%, 84.6. For the median, I have what? 82.7. You can see that the mean is performing better in this case. The most frequent is even performing better than the median. But the constant input, that is, I use a constant, a particular constant to represent the missing value in the data set, and I'm having 87.2%. So with this now, I have been able to what? To know that the best way to handle missing value in that particular feature is to use what? Is to use a constant value. I don't need to use the mean, because with a constant value, I'm having a better performance. Okay. Now, if you do a visualization of that using the box plot, mind you, the box plot, the upper part is what? Is the upper quartile, and this is the lower quartile. You can see that it is the constant that is actually performing better, or a better representation of the missing value. So that is how to handle missing value in your what? In your data set. Now let's look at PPScore and correlation. For PPScore and correlation, we have on my left correlation plot, and on my right PPS matrix. How does this work? How do we want to interpret this? We are plotting a correlation. We are plotting correlation. We are having correlation plot on our Titanic dataset. And for the Titanic dataset, the survived is the what? This feature survived is the target what? Target feature. That is the feature we are trying to predict with the machine learning model. Now, to interpret this, you will see that family size to passenger ID is having a correlation of 0.065. If I go and compare P class and what? Passenger ID, I'm having 0.9. Though the passenger ID should not be be used in this sense, though they are numbers, but they are unique. I mean, they are unique across each entry, isn't it? So they 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 are more like what? They are more like categorical data that are what? That are nominal. They have less structure. Now, but if I come to the PPS score here, for the PPS score is trying to measure the predictive power of each feature. I don't know if you get that. The predictive power of each feature. So again, the survived here is what? Is our target variable, isn't it? And you can see that for me to predict survive, I can use all these features to predict survive. But the best one here is the what? The sex, that is the gender. It means that if you were on that Titanic ship, your gender matters if you will survive or not. Does that make sense? And the beauty thing about predictive power score is I can use the predictive power score to quickly know how to even handle my missing value. For instance, if I have issues with my ticket feature, I can go and use my fair feature to handle that. It means that if I have missing value in ticket feature, I can have the fair value. I can do some computation from the fair to infer the what? The missing value in the ticket value. So the predictive power score tends to what? To handle both categorical data set, categorical data and numerical data perfectly. So we can use this to get insight from our data to know the relationship between features in our data. Now, how can we encode our categorical data? There are several ways we can do that. Several ways you can use to encode your categorical data. And what does it even mean? What's the meaning of encoding categorical data? For now, we are going to focus on the one-hot encoding. For the one-hot encoding, this is a feature. Assume this is a feature. I have my feature to be what? Color. And for the color, I have several entries there. I have red, yellow, and green as what? Unique features in this unique entry in this feature. Now, what the one-hot encoding is trying to do is to have a numeric representation of the features, of the entries rather. In this sense, each of these unique entry in this feature color, which is red, yellow, and green, will become new features each, whereby for the first row, we have red. Under here, it is what? Under the red, we have 1 and the rest will be what? 0. For the second one, we still have red. You will see that for the second row here, we have 1 and the rest is what? 0. Now, we have yellow on the third row. You see that under the red, we have 0 on the third row, but under yellow, we have 1. And under green, we have 0. So we are trying to encode this feature using one-hot encoding. And at the end of this, we have a new feature, each representing the what? The unique entry in the in the feature we are trying to encode. So with this now, this particular feature is ready to go into machine learning model, and we can start training our machine learning model on it. We can't use this direct feature, though there are some algorithms that can handle categorical feature, but it is better you encode sometimes. Now, if you go back to our Titanic data set, you will see that the embark feature is what? Is a categorical feature. It's not a number. They are all categorical, isn't it? Now, how can we encode this feature? How can we encode it into what? Numeric value. Let's use one-hot encoding once more. If you use one-hot encoding from pandas, we have this shortcut called get dummies. Now we are passing in the embark feature there, and you will see now that each of this entry here, QS, we have 3 unique value there, which is CQS. Now we are having what? Numeric representation of what? Of the entries. Now this feature is ready and can be used to replace this feature here. It means that our new embark feature here can be what? Can be replaced with this particular what? This particular features that we've encoded. Now, how do we handle rare categories? What is even the meaning of rare categories? Sometimes we try to categorize. We've already seen in our data that we have categorical value. Sometimes we have some rare categories in the sense that they don't occur frequently. For instance, if we look at the same data set, we'll see that the platform type is what? Is actually a categorical data. And if I check the occurrence of each of the categories, you see that one is about 2,500 represented. I have category 2 less than 2005, but category 3 is having what? About 17,500. So if we try to go and encode this, whichever encoding we are trying to do, we might be passing the wrong message to the what? Machine learning model. So sometimes it will be better to take care of the rare values. For instance, category 4 is very rare here, and even the level of your rareness is now dependent on you. You can say that if the occurrence is less than 10%, if the occurrence is less than 20%, then that is what? Rare. Then you can, one way of handling that is to combine rare values together, rare categories together as a new what? As a new feature. So if I look at this, I have four entries, which is 1, 2, 3, and 4. So if I go now, I've been able to use the fourth category, which is very, very rare. I'm putting it in what? I'm using the data frame.lock, looking at anywhere you see that the platform type is equals to 4, get me the index. Now look for those index and replace them with what? With 2. It means that previously we have category 4, but now we've merged it with what? Category 2, because category 4 is very, very rare. Now this is still not balanced, and is not a good representation of this feature. We can still combine these two together to become what? A single feature. But all this can be done and checked against a model to see which one perform best for you. Now feature transformation. What's the meaning of feature transformation? We look at log transformation, reciprocal transformation, but because of time, we will only focus on the word power transformation. What are we doing with power transformation? Power transformation just try to map pictures from any distribution. We can have Gaussian distribution and any other distribution. So it's trying to map any distribution to be close to what? Gaussian distribution as possible. And what is the meaning of Gaussian distribution? Whereby we have zero mean and unit variance. What do I mean by that? For instance, look at this visualization. This particular data set is what? Is having log normal distribution. This one is having chi-squared distribution, isn't it? Now, with the power transform, using the Boy's-Codd strategy, we have been able to transform the log normal feature or distribution into something very close to what? Very close to Gaussian distribution. Also, if we look at the chi-square, we have been able to use the power transform to transform it to what? Something very close to what? Gaussian distribution. Mind you, the Gaussian distribution is always like is like bell shape. And why are we actually doing this? This is done if we are trying to use machine learning models that prefer to work or are built on what? On normal distribution. So some machine learning model can actually handle any other type of distribution, but majority still rely heavily on the what? the normal distribution. So we try as much as possible to transform our data from any other type of what distribution they can be into what normal distribution. Now, the two power transform strategy are what? They are the Boscott transform and the Johnson transform. What's the difference? The difference being that Boscott transform requires strictly positive input. That is, all the input you are passing through the what? The Boscott transform, all of them should be positive. Why the reverse is the case for what? Your Johnson transform. Your Johnson transform supports both positive and negative data. Now we move on to feature generation and contribution. For construction, feature generation, you need domain knowledge. For you to construct new feature from existing feature, you have to know what is happening in the field you are trying to solve. That is, you are trying to solve a problem in medical field, you have to at least know something about medical field. And if you don't know something about medical field, that is where the domain knowledge comes in. You need to make some you need to do some consulting or make some research about it. Now, sometimes we can apply mathematical computation. We can do some what? We can have features from date and time. So, what do we mean by domain knowledge once again? Domain knowledge is simply knowledge in a specific area. For instance, if I have data set in what? In Titanic now, it is based on transportation, shipping transportation. Yes, water transportation, isn't it? So a sailor or someone on the ship will know have better information than just a mere data scientist that just pick this information, pick the data set up and try to build something out of it. So when you don't have a clear view of your data set or it's not making sense to you, you can work on domain knowledge. That is, make research on the problem you are trying to solve. Now, if we try to do some mathematical computation, let's look at Titanic data set once more and apply what mathematical computation on it. For instance, we are looking at family size. Family size, it says that I have two features in what in the Titanic data set, the sibling and the parent. For the siblings, measuring number of siblings that are with you, the brothers and sisters that are with that passenger. For the parents, is looking at number of parents that are with that passenger. Per child, parents per child. That is the number of parents per. The number of parents per what? Per child. Now, if we add these two together, that gives us what? Family size. This family size is a new feature entirely, isn't it? Is a new what? New feature entirely. So this new feature, if I try to see whether it will be a good feature or not, that is why the predictive power score, the predictive power score is very, very good. Now I've created a new feature called family size. With the predictive power score, I can quickly check how predictive is this family size to what? To predicting the survival of a particular what? Passenger. And you can see that we have 33%. That's a good feature compared to what we are having before. If you look at our PPS score, some features don't have predictive power up to 33%. For instance, if you look at the what the let's look at the embark. For instance, the embark is only having 0.26, that is 26% predictive power. Mind you, the family size we just created now is now having 33%. It means that if you are able to create new features out of the features you have, you might be able to what? To improve your machine learning model. Again, if you look at the Sandy data set, how can we get features from dates? If you look at the Sandy data set, we have a date feature here. We have placement time, we have arrival time. So how can we derive feature from date? If I look at the placement time, for instance, I can use the pandas dot to and call the function to date time. That is, I'm converting it to date time. Now pandas sees this as what? As date time object, isn't it? Now From that, I can try to extract the hours at which that transaction was performed, the minute at which it was performed, the seconds at which it was performed. For instance, you will see that the placement time has what date and what and time. And in the time we have hour, minute and what seconds. So now if I put this into machine learning model, it will not function well. It won't even be able to what? The algorithm will not be able to run. So extracting the hour of the day out of the time is a good idea. I can extract the minutes out of that, and I can extract the seconds out as well. You can go ahead and extract the year, the age, did I say the age? Sorry. The year, the month and the day. So those are the way we can use to extract features out of what? Of date time feature. Okay. Sorry about that. Also, another thing we can do again is feature scaling. How do we perform feature scaling? We can use standardization, and standardization is different from normalization. When you are standardizing your data set, what you are doing is you are changing the range of your data. If the highest value in your data is, let's say, 1000, and the lowest value is like 500, we are trying to change the range of that data from the lower bound to other upper bound to lie between a particular set range. Maybe for instance 0 and 1, or -1 and 1. But for normalization, what you are actually doing is you are changing the distribution of the data. What do I mean by that? I said in the first one that we have there was a slide that we show that we have a what we have log normal distribution trying to go to what? Gaussian distribution. We had chi-square distribution trying to go to what? In trying to go to normal Gaussian distribution using the power transform. Now if we that is we can use normalization. Normalization is trying to change the distribution, while standardization is changing the range of the data. This is what I mean. I have what? This normal distribution. If I standardize this, I will have the mean to what? To be what? To be 0, and the what? The standard, the variance to be 1. Once you standardize your data set, what it means is that you are changing the mean and the variance, everything to lie between a particular chosen range. So if I'm using the standard scalar, for instance, if I'm using the standard normalization, it means I'm having the mean to be what? 0. This is the mean of the distribution, and I'm having the what? The variance to be 1. But when I'm performing normalization, what I'm doing is I'm changing the distribution of the data. If you see the distribution here is different from the distribution I'm having here, isn't it? But for the standardization, the distribution remains the same, just that the mean and the variance now are what? 0 and 1. If we look at this again from the data set, let's use this dummy data set, this sample data set. I am now using the hour, the minute and the seconds we created the last time. If we call the dot describe method on this, I can have the what? The mean here is, the mean of the hour is 12 hour, the mean minute is what? 29 minutes, and the mean seconds is what? 29 seconds. If you look at this standard deviation as well, they are all different. What we want to do now is to standardize. We want the mean to be very close, or if not 0, to be very close to 0, and the standard deviation should be what? 1. How can we do that? How can we achieve that? Again, if you look at the box plot, we can quickly see that for the box plot, the middle of the box is the median. Almost the minutes and the seconds here have almost the same median, but the hour is having a median of something like let's say 12. So we need to standardize this to have the same mean and the same what? Standard deviation. So from scaling, we can use the standard scaler. The standard scaler can be used to standardize our data, in the sense that once I standardize now, I can have, sorry, okay, I can have what? You will see now that the mean is what? The same value. And the standard deviation is also what? The same value. The mean is what? Almost 0. And standard deviation is what? 1. If you look at that on our box plot now, you will see that everything is having almost the same mean and what? The same variance. So now our data has been what? Standardized, and machine learning model can perform well on standardized data. Okay, so at this juncture, I think I've taken so much time, and for further reading, you can look at Feature Engineering Codebook. These are good books, and you can also look at Feature Engineering Made Easy. These are good books that will give detailed explanation on what I've tried to explain and those I've not been able to cover. Okay. Thanks for having me again. You can check out, ask me any question on Twitter, check some of my Medium posts and some of my work on GitHub. So thank you.